So, I mean, these are all the essential learnings from the SOLs, the standards of learning, and and some of it, like when it comes to polynomial functions, which we did some of this in here. In fact, we kind of did more of it in the last unit, so we don't have to dwell on that. We just have to like look at the things that we haven't done so far. But you can see these are the kind of function stuff that we're supposed to know. And this SOL, I think it's the Algebra 2.8 right here. You know, when they say that, they don't give you a kind of function. It's more general than that. But the reality is that most of the time, their problems have to do with logarithms and exponentials. You know, when they talk about asymptotes, all the questions that I've seen have come from that. There are other kinds of functions that have asymptotes, but usually the question will be related to exponentials and logarithms. That's why this is the place we want to do it. So we already knew something about domain and range. We already knew something about a zero. What's a zero of a function? Yeah, it's the x-intercept. It's the value of x that makes the y value 0. Things like that. This is where we first got into restricted domains, meaning that there's actually times when you can't plug in anything you want for x. And there was actually 3 situations that we encountered. One of them was can't divide by 0, right? And we're going to talk about that one. It's also square root of a negative, but that's not going to be part of the test. Okay, so we won't worry about that one, but that is actually a restriction on domain. If you're taking the square root of a variable expression, you have to make sure you're not taking the square root of a negative number. And then we actually learned of a new restriction to domain in the course of the unit, and that was logarithms, right? This domain is not all real numbers, so that means there's a restriction. You can't take the logarithm of a negative number or 0. Right. So intervals of increasing and decreasing, right? That's something actually we get more with the polynomial function. And vertical and horizontal asymptotes, we've seen them both so far with exponentials and logarithms, and end behavior. And end behavior is sometimes with a polynomial, sometimes with exponentials. But then it could be about another kind of function that we're going to get to in a little bit. But all right, polynomial functions. Most of what we did with polynomials was what we did in the last unit. It just said it didn't really include any of the function stuff. But when you mean function, you mean graphs. And that's just the way these units are designed, unfortunately, because you know, then when you try to go back and take the things that are related to the graphs of polynomials, you find that the book is kind of wanting in that. But you know, the one thing besides increasing and decreasing in end behavior is the other was the concept of multiplicity, right? What does it mean to say that a 0 has a multiplicity? So that we've got to review too. Then you get something that kind of stands alone a little bit is you know, function operations, compositions of functions, and then inverses. And those all come up in here. And then we get into our exponential and logarithmic functions, which have a significant part of domain and range, restricted domain because of logarithms, asymptotes, and the fact that they are inverses with each other is something we're supposed to know. And then we get the last thing that was introduced in this lesson, but we end up doing it with so many different, in this unit, but we'll end up doing it all through the year as transformations. How is it that you shift the graph of a parent function? I mean, honestly, we've done most of these already. I think the square root function we didn't do so far. We didn't do inverse variation, but most of the rest actually are things we've already dealt with. We always start this with absolute value when you do transformations. So let me go ahead and do. So polynomial functions, let's review what we mean by these things. Put that in a blue. My little finger is so small I can barely see it. And I think I brought this up here. So a polynomial function, this was in the first lesson that we did. If the degree of a polynomial is n, right, that we learned in the last unit is then how many zeros does it have if it has a degree of n. N. It has exactly the same as the degree. Some might be real, some could be imaginary. So the number of real zeros is less than or equal to n, right? There's going to be a total of n zeros. The number of turning points in the graph can be up to n minus 1, right? So a linear is degree of 1. It has no turning points. It's just a straight line. A quadratic is degree 2. It's a parabola. How many turning points? 1, right? A cubic can have 2. A quartic could have 3. It could have less than that too. You take something like a cubic function, it could look like, here, this could be a cubic function. I mean, this is y equals x to the third. I mean, you'd probably look at it and say it doesn't have any turning points. I mean, it is actually increasing from one side to the other. So by that definition, it doesn't. But that's why it's less than or equal to n minus 1. I mean, that helps us just to figure out the shape of the graph. Okay, by multiplicity of a zero, what we mean is if the factor that the zero comes from is raised to a power, then if it's greater than 1 is usually when you start calling under multiplicity. And it makes the graph look different for that zero, whether or not it's being raised to an odd power or to an even power. Right? If it's an odd power, it's going to look like the graph goes right through the zero. It changes sign because it's being raised to an odd power. If it's an even power, like y equals x squared, right, it stays on the same side of the x-axis because it doesn't change sign. And that's more general than just, quadratics. Anytime you raise a factor to an even power, that's what you're going to get out of that zero. Right? We know that intervals of increasing and decreasing, and this is almost always done with a polynomial function, that means intervals of x. Right? Don't get confused by whatever the y values are of the turning points when you see it changing direction. It only means the x values. And we've done this since the beginning of this unit, and it has not seemed to be an issue. That most have been pretty good about not trying to say the y values. They've stuck to the x values. And then the last thing, which is a graphic from the book, is this end behavior. How do you tell what the end behavior is of a polynomial? And by end behavior, what do we mean? It means what's the graph doing on the extreme right side of the x-axis and extreme left side of the x-axis. And it's usually written like this, right? As x, and the arrow means approaches, as x approaches negative infinity means as x is going to the left of the y-axis in the direction of the left, right? That would be towards negative infinity. Right? Always on the left side, x is approaching negative infinity. And then the f of x means what's the y values doing. And in this case, the y values, since the graph is going down, the y values are approaching negative infinity. As x approaches positive infinity, it looks like the y values are approaching positive infinity. So that's how we write end behavior, right? You need to know that kind of notation and give answers like that. What this is telling us is that in general, right, we don't have to memorize it just for 1 or 2. In general, if the degree is odd, like linear, like this cubic, that means that it's going to have an end behavior which is either negative on this side and positive on that side, or positive on this side and negative on that side. Anytime that the degree is odd. Now, how do you know which one it'll be? You know it by whether or not the leading coefficient is positive or negative. Okay, leading coefficient is positive, it'll go like that. Leading coefficient is negative, it'll go like that. Right, and this is a graph of what we presume is a cubic, but any odd power, it would work the same way. Right? If the degree is even, then we know that the end behavior will either be positive, positive, or negative, negative, right? How do we know which one? If the leading coefficient is positive, right, like a quadratic function which starts with ax squared and the a is greater than 0, then it's a parabola that opens up, right? If the leading coefficient is negative, then the parabola opens down, or the even degreed polynomial function opens down. You know, this book doesn't call it this, but in other books they call this the leading coefficient test, LCT, the leading coefficient test. And just supposed to give us some kind of basic understanding of what we're looking at in the shape of the graph. Right, so if I know that, right, what is the end behavior? I know how many real zeros it could have. I know how many turning points it can have. I know a lot about the graph of the function at that point. What do you think the degree of this is? They didn't say, but what do you think the degree of the bottom two are? How many turning points do you see? 3. So it could be, at the least, it could be a 4th degree polynomial. It could be 6 or 8 or whatever, but we just don't see the turning points going on. But let's just say it's a 4th degree polynomial. How many real zeros do you see on that? Right? Real zeros show up on the graph as x-intercepts, so it's 2. Okay? So what does that mean the other 2 are? They're, you know, in the terms of the SOLs, they would say non-real. They're imaginary, right? So you could see there, if this is a 4th degree polynomial, and that means 4 total zeros, 2 are real, then the other 2 have to be imaginary. And what do we remember from the last unit? What do we know about imaginary zeros? They occur in pairs. So that makes sense. Two imaginary, that fits. We don't have any issues with that at all. Okay, I think that's that. Let me go back to this now. So increasing and decreasing, multiplicity of zeros. Let me draw the multiplicity of zeros. Well, let me just do one. I'm gonna draw this one like this. 1, 2, 1, 2. So okay, so what are the zeros? Looking at that graph, what are the zeros? Yeah, -2, 0, and 2. Okay, so you should look for the x-intercepts. 0, or -2, 0, and 2. But again, look at the graphs, right? These 2 zeros, the graph is going right through the 0. It's changing sign, going to the opposite side of the x-axis. But that one is not. What does that tell you? Say again? What's the multiplicity of that going to be? Even, right? It's even. You don't necessarily know it's 2, but it's probably 2, right? But it's even in any case. That's why it stays on the same side. So we would expect, if this was a polynomial function, that it might look something like this. Y equals x squared. There's the multiplicity, which is even, and x plus 2 times x minus 2. Okay, what about the intervals of increasing and decreasing? How many turning points is there? It looks like there's 3, which means it has 4 intervals. Go back to blue. Okay, how do we describe this interval, which is increasing from the extreme left side of the graph until it gets to x equals -1? What's that interval? The left side of the graph is -infinity, and it's stopping increasing at which x value? -1. We're estimating -1. Okay, what is this interval here where it's decreasing? From -1 to 0. right? And then what is this interval of increasing? 0 to 1. And then what is this interval of decreasing? Starts at 1 and goes to infinity, like that. So that just gets at a little bit what do we mean by increasing, decreasing? We didn't talk about end behaviors. We did that on the last slide, multiplicity of zeros. Okay, next. Okay, transformations. Remember that the absolute value graph is a V, right? If you put down something that's not a V, then we're going to miss most of the credit, because that's something we should understand. It's a V which is symmetric, right? Each side of the V has a slope which is plus and minus the same number, right? So we know that of the basic function, the parent function, and then transformations are, what does it do to that function? If I multiply by a number outside the function, if I add or subtract inside the function, if I add or subtract outside the function. Right? These were all the things that we said we learned about that. Not just for absolute value, but for any of them, right? If the A is greater than 0, that means the V opens up. If the A is less than 0, it means the V opens down. If the absolute value of the A is greater than 1, it's going to stretch it, right? It can stretch it up or it could stretch it down based on the sign, but that's why it's absolute value. If the absolute value is less than 1, it's going to be a shrink, right? It'll make it go up slower or go down slower if it's opening down. Right? When we see a minus a number inside the function, that means right shift. If we see a plus a number inside the absolute value, that means left shift. Right? Outside the absolute value, plus means up, minus means down. These are just reviews, so hopefully. Function operations. We added, we subtracted, we multiplied, divided, and then we took compositions, which was a new thing. So remember, for the subtract, make sure that if you're subtracting a function which has more than one term, you got to make sure you're subtracting all those terms. It's going to flip the sign. Right? And if you divide, be careful not to divide by 0. Right? When you're dividing by a variable expression, that's a possibility. So how do you tell which values are not in your domain? Right? You find the zeros of the denominator, set it equal to 0, solve. And then you need to say x does not equal, whatever they are. What if they don't? What if there are no zeros of the denominator? Then it's all real numbers. Right? Now, composition of functions means we're putting a function inside of a function. Remember that the notation of a composition of function is this little open circle in between an F and a G, right? Which is usually rewritten to look like that. In either case, you say F of G of X. Okay? And you could be asked to find the composition of functions, which means the result is going to be another function, something that's got X in it. Or you could be asked to evaluate a composition, something like F of G of, and then there's a number in there. Right? That was a somewhat easier problem because at that point you don't have to go through all this mess. You just evaluate the G function and plug that into the F function. So we need to know how to do both of those. Right? I think we did both of those on the quiz that we took. Inverse functions. Right? A function and its inverse undo each other. Right? You know, if we did a mapping diagram and had all the arrows pointing from the domain to the range, the inverse would point from the range to the domain. One explanation of it that I didn't say, I've said in years past is, let's say you have a job, you're making $8 an hour, right? And you say, how much money do you make if you work 10 hours? And you say, $8 an hour, 10 hours means 80. The inverse would be, okay, you have a job, you make $8 an hour. How many hours did you work if you got $160? 20. That's an inverse. They go in opposite directions. Okay? So if f of x equals y, it should be that the inverse of f of y equals x, right? Point in opposite directions. It switches the domain and the range. Like if you have a graph and there's points on that graph and the function, if you switch the x and the y coordinates, you should have a point on the inverse. And the graphs, this is one of the SOL items, right? We should understand that that means that these graphs will look like they are reflections across the line y equals x, the identity function, which we kind of saw that here, right? This and this. This y equals x is a line of symmetry between those two. You just got to tilt your head and it's there. Okay, exponential functions are either growth or decay. The parent function has an asymptote, which means a line on the graph. It's not the graph of the function, right? But it's a line on the background there that the graph of the function will approach without touching. It'll get infinitely close, but it'll never touch it. Right? It has that at y equals 0. The domain is all real numbers all the time. At least for the parent function, the range is y greater than 0. It's above the middle. It's greater than the asymptote. And then again, we can transform that by multiplying by a number, adding and subtracting inside the function, adding and subtracting after the function. Now, which one of those shifts, if you have this kind of a graph, right, is going to move that horizontal asymptote? The vertical shift, right? If you go up or down, that's going to move your horizontal asymptote. And if it changes the asymptote, it changes the range. What's another shift? What's another transformation that would change the range, not including going up and down? What would happen if I just put a negative in front? Right? If a is negative, what does it do to the graph of any function? It flips it across the x-axis. Okay, now what's the range? Y is less than 0. So there actually is another thing we could do to change the range. Okay. Logarithmic functions, right? Logarithms, we should understand, are the inverses of exponential functions. Their parent functions have a vertical asymptote at x equals 0, like is drawn on the board there. The domain now is x greater than 0, greater than the asymptote. The range is all real numbers, and it could be transformed. Right? The one that we didn't see much is what would happen if we had an a. Every one we looked at, a was 1, and it will be that way in the test too. But in fact, I don't think it's wrong not to address that here, because I think that's something that's well addressed in the next level of class. It's not in the SOL. Okay, which one of these shifts is going to move the asymptote and therefore change the domain? A horizontal shift now. So inside the function, if you add or subtract, that's going to shift, just like it did in the homework. Okay, you need to know how to convert from one form to the other, right? We did the one last night, or in the homework that we just checked. We went from logarithm to exponential. So what about this one right here? If log base 3 of 81 equals 4, write that as a exponential form. That would be 3, same base. Exponent is whatever the logarithm equals, 81. Right? What we didn't do is, like on the top, convert that exponential form to logarithmic form. It's a log. It has a base. What is the base? Okay, and what is the logarithm equal? The exponent, so that leaves 64 to go in the middle. And then I think this is my last one, I'm not sure. The evaluating logarithms, right? We did those. They had the one set of problems in the homework where they said, do this without a calculator. And in every case, it was something like 7 to the x is 49. I mean, pretty basic stuff. Usually these problems are a little more than that, and we should understand how that works. even though in the end, for that part of the test, you'll have a calculator to use. You're not going to have it for the whole test, but you'll have it for that part. If you remember where the log base function is to evaluate something like that, that's okay. But this is the more general way that we get these kinds of problems, and we have to evaluate. You remember how we did the others. First, we set it equal to x, because that's what we don't know. Right? Then we converted it to an exponential, and we do. So that's 27 to the x equals 9. Now, that's not something you probably can just look at and say, oh, that means x equals something. But these kinds of problems, when you see them, they're always using numbers that are clearly powers of some smaller base. Like, what number is both 27 and 9 a power of? 3. So you change it to the same base. Right, this is 3 to the third to the x. This is 3 squared. You know, properties of exponents would tell you when you raise a power to a power, you multiply, right? So that's 3 to the 3x equals 3 squared. So now we got an exponential on the left and an exponential on the right, and they have the same base. So it must be that they have the same exponents too. If this is equal to this, it must be the exponents are equal. So you can write yourself an equation which is 3x equals 2, which means x equals 2/3. What if we tried to do the same thing here? Set it equal to x. Sorry, this thing is starting to mess up. 125 to the x equals 625. Right. What number, 125 and 625 are powers of some smaller number. What number is it? 5, right? So it's 5. What power of 5 is 125? So that's 5 to the 3x. And 625 is 5 times 5 is 25. 5 times 5 is 25. 25 times 25 is 625. So that's to the 4th. 5 to the 4th. And since it's one side equals the other and the bases are the same, that means the exponents are the same. So I want to show you that. There is going to be something on there to evaluate on the test. And you could do it like this. There's a couple problems in the study guide to practice that you could see. If you remember where the log base function is, you can use that too. Okay, but you can't ask me during the test then to actually show you the log base so you can do it. You need to figure that out now. Where's the log base function? Okay, I think I'm almost done. But make sure you know how to use the calculator, right? To graph functions, put it under the y equals. You know how to, polynomials at the very least, you have to be able to raise things to a power, right? Not always squared, right? You have a squared button over here, right? But what if you want to raise something to the third power? You have to use the caret key, right? Actually, you're not going to need it for the absolute value, but you could use it for exponential and log. You would need to know the caret key for the exponential, for sure. And the logarithm, you need to know these two, right? Log and ln, and then you need to know how to find, what am I doing here? Oh, that's not the calculator. That's just a picture. Okay. So I'm going to give you a study guide to work on in class. You can work together in that, and I'll make sure you've got answers before you leave, and that's what you should work on. Some of it I had to make up problems because I didn't think the book had any great problems for it, and some of it does say do these problems in the book. Okay.